This is YouTube homework number 5. A. Compare the net force on system A to that of system B. So the net force of system A and B are going to be 0 because by Newton's second law, 0 acceleration meaning 0 net force. And the forces acting on system A have to be greater because system A is more massive. B. Draw a free body diagram for system A and B. So this is kind of blurry, but there's a normal force of the table on A. There's a pushing force of the hand. There's a gravitational force. There's a kinetic friction force of the table on A. And there's a pushing force of B on A. Um, for system B, there's a normal force of the table on B. There's a gravitational force. There's a kinetic friction force of the table on A, on B, and there is a force of A on B. Is the magnitude of the forces exerted on system A by system B greater, less than, or equal to the magnitude of system B exerted on A? So I said that the magnitude of A on B and B on A are going to be equal because by Newton's third law, forces come in pair with equal magnitude, and then they're interacting, which means that they're falling under Newton's third law, action-reaction pair. Um, would your answer change if the hand were pushing system B to the left? So I said no. My system will still be the same. My answer will still be the same because A and B are still in contact with one another. They're still interacting. They still exert forces on one another with equal magnitude. Therefore, Newton's third law still apply. Identify all the Newton's third law force pair in your diagram. Um, so I don't know, something wrong with the quality of the picture, but there's an X on the force of B on A, and there's another X of the force of A on B. Um, what criteria did you use to identify the force pair? So I look for contact or interaction between the two objects, or when I label them, I look for like an opposite of agent and object. So this is A on B, and this is B on A, and this is A on B. So which means that they're acting on one another. So that is a criteria. Um, so my answer for part C is consistent with Newton's third law, action-reaction force pair. That is, the force on A exerted on B is equal to the force of B exerted on A as long as they're interacting, regardless of the direction of the push. So these two have the reaction force pair. Part E, rank the magnitude of other horizontal forces that you identify on your free body diagram. So I got the F push as the greatest, and then the kinetic friction force of the table on A, and then the force of A on B is equal to the force of B on A, which is equal to the force of the kinetic friction of the table on B, and they're all equal. So yes, I did apply Newton's second law. Constant speed equal to zero acceleration, and then zero net force. So all the sum of all the forces have to cancel out one another. So there is no acceleration. F net equal to mass times acceleration. So the greater mass, meaning a greater net force. So the magnitude of the forces of block A have to be greater than the forces acting on block B. So the forces vector on block A have to on system A have to be longer. Um, yes, I did apply Newton third law. So I have an action reaction pair. That is the force of A on B is equal to the force of B on A. So they're action reaction pair. So they have to be equal by Newton third law. What information beside Newton law did you use to apply in comparing the magnitude? So I assume that the block are made of the same material so that their coefficient of friction are the same with the table. So since friction is mu sub k multiplied by the normal force, so the greater the mass, the greater the normal force. And since mu sub k is constant, then the friction force on A have to be greater. So determine the magnitude of each of the forces that you drew on your free body diagram. So this is my equation for system A. So the more normal force on A is equal to the gravitational force on A. And then for the x direction, I have the pushing force is equal to the kinetic force plus the force of B on A. For system B, I got the normal force on B is equal to the gravitational force on B. And then the force of A on B is equal to the kinetic friction force of B, which is mu sub k multiplied by the normal force. And then solving for all of these, I got that the F push is 15 Newton. The F of A on B equal to the F of B on A, which is equal to the kinetic force, friction force of the table on B, which is 5 Newton. And then the kinetic friction force of T of the table on A is 10 Newton. So even if you have the speed, then I would say that the answer would still be the same because the forces only depend on acceleration and not the velocity, which is speed. By Newton's second law, F net equal to ma. So therefore, there would be no change in the forces. Section 2. A. Describe the motion of the system of A and B. How does the motion compare to that in part 1? So the system of A and B would accelerate, so now there's less friction force to counteract the pushing force of the hand, assuming everything is stayed the same. Compare the net force, magnitude, and direction on system A to that of system B. So the net force of the two systems are not zero anymore since they're accelerating. Since system A is more massive, the forces exerted on it are greater in magnitude compared to system B. So F net of A is equal to 2 F net of B. And this is my free body diagram, my new free body diagram. There is still a normal force, a gravitational force. The pushing force is still the same. Everything stays the same except the kinetic force, kinetic friction force, which I made them a little bit shorter. And you can see that the F net is not zero anymore. The right side longer than the left side. So I don't agree with any one of the student. Student 2 is right about the accelerating motion, but the forces that A but the force that A exert on B and B exert on A are still the same. They're still interacting with one another and follow Newton number 3. The system accelerate only because of the less friction force, and that have nothing to do with the internal forces that they exert on one another. So this is my new ranking. So the F push should be the greatest, and then the force of A on B equal to the force of B on A, greater than the kinetic friction force of the table on A, greater than the kinetic friction force of the table on B. So now the block accelerating, the forces on the right have to be greater than on the left. So this is Newton's second law. The forces on A and the forces of the force of A on B and the force of B on A have the same magnitude, since their action-reaction force pair. So this is Newton number 3. Since force and mass are proportional, therefore the forces acting on system A, which is more massive than system B, uh, have to be greater in order for the two systems to have the same acceleration. This is also Newton number 2. Section 3. A. Compare the magnitude of the net force on system C to the net force on system A and B. So the magnitude of the net force on system C is the same as in system A and B. Since the forces of A and B is the same as B on A, which means they have the same acceleration. They're internal forces and can be ignored. And the external forces acting on the system are the same. The only difference is that we're analyzing the system as a whole. So there's still a pushing force and there's still a kinetic force. So that leads to my free body diagram. So I have a normal force, a gravitational force, a kinetic friction force, and a pushing force. So the F push in both cases correspond to one another. The normal force of the table on C corresponding to the normal force of the table on A, and plus the normal force of the table on B. The kinetic friction force on C correspond to the kinetic friction force on A plus the kinetic friction force on B. The gravitational force on C correspond to the gravitational force on A plus the gravitational force on B. So I did not include the force of B on A or the force of A on B, since they're action-reaction force pair, which we learned in class that they would cancel one another out and does not have anything to do with the net force of the system. So this is my sketch of the free body diagram for the car. So I have a table and a car sitting on the table and a rope pulling at an angle. So my description for the situation is that the car it being pulled up to the right of the table surface indicates by the magnitude of the gravitational force being greater than the normal force, which means that the car it being lifted up at an angle and to the right.